There is a place in Wyoming where tourists drive for hours to photograph a rock formation that looks exactly like a tree stump. Not vaguely, not if you squint exactly. The columnar structure, the ring-like banding at the base, the way the top is flat and slightly concave, the way any stump looks after the wood has weathered away, and only the compressed, mineralized core survives. The Park Service calls it a volcanic plug, an igneous intrusion. They explain the hexagonal columns as a result of cooling lava contracting, which is true of basalt, which does form columns under certain conditions. What they do not explain is why it looks precisely, structurally, undeniably like the stump of something that once grew there, and why, once you start looking for formations like this, you cannot stop finding them. Devil's Tower is 867 feet tall. It rises from the Wyoming plains with no geological relatives nearby, no mountain range, no volcanic field, no lava flows radiating outward in any direction. It simply stands there, isolated, its base surrounded by a debris field of the same columnar material that forms its walls, as if something shattered and fell around it over an enormous span of time. Every other volcanic plug on this planet sits inside a volcanic system. This one does not. That anomaly has a standard explanation. The explanation is that the surrounding rock eroded away over millions of years, exposing the harder core. That is possible. Erosion is real. What it does not account for is why the debris field around the base looks less like eroded mountain and more like broken wood. The rangers have a term for those fallen columns. They call them logs. This is not a fringe idea. It is documented in geology papers, in the photographs of 19th century surveyors, in the folklore of every indigenous culture that ever lived near one of these formations. The Lakota call Devil's Tower Bear Lodge, and their traditions describe it as something that grew, not something that erupted. Something that grew and was then, in some stories, cut. You can choose to read that as metaphor. Most academics do. But the alternative reading is that the metaphor survived because it was accurate. The theory is this: the Earth once supported a biosphere of a scale we cannot currently imagine. Trees, or organisms that function like trees, reached heights measured not in hundreds of feet, but in miles. 40 miles is the number that circulates in the research community that takes this seriously, based on atmospheric pressure modeling and the structural requirements of what we would need to find to explain certain geological formations. Those organisms are gone. The stumps remain. We call them mountains. We call them mesas. We call them volcanic plugs and igneous intrusions and erosion remnants. We have never seriously considered that they might be the compressed, petrified bases of a living system so large that our entire recorded history fits inside the gap between when it died and now. Before you dismiss that, follow the specific evidence, not the theory. The evidence. In 1878, a survey team mapping the American Southwest documented a series of flat-topped formations in Nevada and Utah. Their notes describe the rock as having a fibrous interior structure, unlike any volcanic material in their geological reference library. One surveyor, a man named Clarence Dutton, who spent 12 years mapping the Colorado Plateau, wrote that certain canyon walls displayed a layering pattern that reminded him repeatedly and uncomfortably of cross-section wood. He published this observation. It was noted by his contemporaries, and then it was quietly absorbed into the literature as a curiosity, explained away as pareidolia, the human tendency to see familiar patterns in random forms and never seriously investigated. Pareidolia is a real phenomenon. It explains why we see faces in clouds. It does not explain why trained geologists with decades of field experience independently note the same structural anomaly in the same class of formations across 3 different continents and arrive at the same uncomfortable comparison. Consider the Deccan Traps, the largest volcanic province on Earth, covering roughly 200,000 square miles of the Indian subcontinent. The standard model says a mantle plume erupted approximately 66 million years ago, coinciding with the extinction event that ended the Cretaceous period and produced one of the most significant geological features on the planet. The basalt flows are between 6,500 and 8,200 feet thick in places. That is not a mountain. That is a continent of compressed rock sitting on top of other rock. And the dating of the layers shows something interesting. The lower layers are older, the upper layers are younger, which is what you would expect from a volcanic eruption, lava flowing outward and upward over time. But it is also what you would expect from a compression event, something enormous, settling, compressing, mineralizing from the bottom up over millions of years. Both explanations fit the data. Only one of them has ever been seriously funded. The oxygen question is where this theory gains the most traction with researchers who will not put their names on it publicly. Current atmospheric oxygen sits at roughly 21%. In the Carboniferous period, approximately 300 million years ago, it reached 35%. Insects grew to the size of eagles, dragonflies with 2-foot wingspans, millipedes 8 feet long. This happened because oxygen was abundant enough to support metabolisms we do not see on Earth today. Now, ask the question in reverse. If the atmosphere supported fauna of that scale, what supported the atmosphere? Oxygen is produced by photosynthesis. The oxygen spike of the Carboniferous required photosynthesis on a scale that current flora cannot explain. Current models attribute it to vast coal swamp forests of lycopsids, tree-like plants that reached heights of around 150 feet. That is the official explanation for a 35% oxygen atmosphere. 160-foot trees in swamps, generating, by some models, 10 times the oxygen biomass of current forests. From plants, a third the height of a modern skyscraper. That math has always bothered atmospheric scientists who work on deep-time climate modeling. The numbers require either an implausibly dense global forest of 160-foot plants or a relatively sparse distribution of something significantly larger. Nobody publishes the second option. The first option is the one in the textbooks, the one that generates grant funding, the one that produces academic careers. But the numbers still do not close. Go back to the formations. The Giant's Causeway in Northern Ireland. 40,000 interlocking basalt columns, hexagonal, rising from the sea. Official explanation: a volcanic fissure eruption approximately 50 to 60 million years ago. The lava cooled and contracted into columns. This is the accepted geological account, and it is defensible. What is interesting is that the columns average 10 inches across and are remarkably uniform in size. Natural cooling basalt produces columns, but the uniformity of diameter across 40,000 individual structures is unusual. More unusual is the fact that the same formation, the same hexagonal columns, the same diameters, the same structural characteristics, appears at Fingal's Cave on the Scottish island of Staffa, 120 miles away, and at the Svartafoss waterfall in Iceland, and at the Alcantara Gorge in Sicily, and at Cape Raoul in Tasmania. All of them produce the same explanation: cooling lava. All of them show the same structural uniformity that makes geologists who study crystal formation quietly uncomfortable. There is a term in materials science for what happens when organic matter is compressed and mineralized over geological time: permineralization. Silica or calcium carbonate slowly replaces the original biological material while preserving the cellular structure. The result looks exactly like rock. It is chemically rock. But under a microscope and specific imaging conditions, it retains the structural memory of what it was before. Petrified wood is the most familiar example. We find petrified logs everywhere. We have entire forests of them. We accept that wood can turn to stone. We do not accept that a structure 42 miles tall could turn to stone and still be standing. Mostly because we cannot imagine anything 42 miles tall ever existing. But scale has nothing to do with the chemistry. Permineralization does not care how tall the organism was. It only cares whether the conditions were right. Now here is the specific geological claim that researchers in this space point to most often. Mountains that fit the stump hypothesis share a cluster of anomalous characteristics: flat or concave tops, circular or near-circular bases when viewed from above, internal columnar structure rather than the layered stratigraphy typical of sedimentary or volcanic formations, debris fields of the same material at the base, oriented as if something fell outward from a central point. Absence of the geological context you would expect for the official explanation: a volcanic plug without a volcanic field, a mesa with no obvious erosion source for the missing material, a granite intrusion with no associated magmatic event in the regional record. Each individual anomaly has an individual explanation. Take them together as a category of formation, and a different pattern emerges. Not proof. Pattern. The difference is important. Proof would require a sample, a preserved section of the original organism, a root system, a molecular analysis that confirms biological origin for material currently classified as purely geological. Nobody has done that analysis, not because the technology does not exist, it does, but because no research institution has funded it, and no institution will fund it until a credentialed researcher publishes the hypothesis in a peer-reviewed journal, and no credentialed researcher will publish it without funding. This is not conspiracy. This is how normal science fails to investigate things that fall outside its categorical assumptions. What we do have are the anomalies themselves, the tepuis of Venezuela, sandstone table mountains rising thousands of feet from the jungle floor. Their tops are isolated ecosystems, biologically distinct from everything below, because they have been isolated so long that separate evolutionary lineages developed in place. The official geological age of these formations is in the billions of years for the underlying rock, but the current surface structure is far younger. What interests the stump researchers is the base structure. Each tepui is roughly circular. Each has a nearly vertical wall that transitions sharply to the flat top. Each has a base that shows a different weathering pattern than the surrounding terrain, as if the material there is fundamentally different in density and composition from the rock it sits on. Standard explanation: differential erosion of harder sandstone relative to softer surrounding material. Possible. Also, exactly what a cross-section of a mineralized root system would look like relative to surrounding soil that had over time become rock. Shiprock in New Mexico, a 1,583-foot volcanic plug rising from a flat plain, accompanied by 3 radial dikes extending outward from its base. The official explanation for the dikes: magma flowing through cracks in the surrounding rock during the original eruption, hardening in place, then exposed by erosion over millions of years. which is consistent with the geology. What is inconsistent is the angle. The dikes extend outward and slightly downward from the central structure. Magma, flowing from a central source through horizontal cracks, would be expected to spread radially at the same elevation as the intrusion. These run downward, which is what root structures do, which is what nothing volcanic does. None of this is in a textbook. None of this will be in a textbook until someone with institutional backing, peer review, and a career they are willing to risk asks the question formally and funds the imaging. The technology to settle this exists. High-resolution internal scanning of geological formations, the same technology used to find hidden chambers in the pyramids, could be applied to any of these structures in a matter of weeks. The cellular structure of premineralized biological material is distinct from volcanic crystalline structure at a microscopic level. You would know within months whether Devil's Tower is a cooled magma plug or the stump of something that once grew there. Nobody has looked. That is not a conspiracy. A conspiracy requires intent. This requires only inertia. The category exists. The funding structures reward research within the category. The formations sit in their national parks, their photography making them famous, their nature unchanged, their actual composition never seriously interrogated. Beethoven's tuning fork vibrates at 455 Hz in a glass case in the British Library. Every piano in the world is tuned to a standard he never used. The bells that once held a different frequency melted into cannons. The buildings designed to resonate with those bells still stand. The stone still carries the architecture. Nothing feeds it anymore. The trees, if they existed, are gone. The stumps remain. The stone still carries the structure. Every hiking trail on the planet runs past formations that might be the most significant biological remnant in Earth's history, labeled with plaques explaining volcanic activity and erosion timelines, photographed by tourists who post them without asking what they are looking at. The question is not whether this is true. The question is whether anyone with the tools to find out has ever seriously tried. The answer, so far, is no. And the reason that answer should bother you is not because it suggests a cover-up. It suggests something quieter and more fundamental. That science, like every other human institution, has categories. And what falls outside the categories does not get investigated. It gets labeled. And the label sits on a placard next to a hiking trail, while the thing it describes keeps standing there, waiting for someone to ask the right question. We have the stumps, we have the imaging technology, we have the chemistry. What we do not have is the will to look, because looking would require admitting that the map we have been using is missing an entire continent, not of land, of time, of scale, of what this planet once held and no longer does. And the people who drew the map have been dead for longer than the trees.